Hey, juniors, how's it going? We're going to talk about soils today. So last week we talked about weathering. We talked about how we break it down, right? So whether physical or chemical weathering, there's different processes that are involved there, and we kind of did an overview of those, and then you were looking at chemical weathering specifically on tombstones, thinking about weathering rates and how climate affects weathering. Um, this week, we're going to look at soils. And in Mrs. Bates' class and in my class for the next couple of weeks, we're going to be looking at soils in a little more detail. So this week, we're going to look for sure this week, we're going to look at sediments that make up the soils, specifically grain size analysis and so forth. Um, I think this week, we're going to focus primarily on the grain size analysis and characterizing the composition of a sediment. And then following the next week, we'll look more at statistics. And then finally, we'll spend some time looking at the actual stuff that clays come from in the soils, because that's the more mysterious part of a soil. Let's talk about that for a moment, though. I've got this little presentation here. So what is a soil? A soil is made up of a number of different things. You've got the regolith itself, which is the loose rock, or the bedrock, which becomes the loose rock that's broken up through weathering. And then you've got some organic matter that develops over time and accumulates over time, water, liquids. There is, of course, open space filled with gases. Part of the atmosphere is down there, and then other mineral grains and so forth that are products of chemical weathering and physical weathering. And so these are the big primary components of a soil. It's a mixture of things, right? So let's bring back that term critical zone. Soil is a place, another place where the spheres are interacting and causing stuff to happen. And the critical zone, why is it critical? Because it's critical for life. It's where all the biogeochemical cycling interacts. It's one of these like I don't know, these nodes of exciting stuff going on, right? And it doesn't look that exciting because it takes a long time to happen and whatnot, but it's very, very important. You don't eat without soil, right? We don't, we couldn't live without it. And it's very important we understand um, as much as we can about it and how to protect it and so forth as well. And so you'll be learning about from an agricultural standpoint and Mrs. Bates' class quite a bit. And we're both going to be talking about soil texture. But these are the main components, right? And so different soils have different amounts of these components. If we focus on the solid matter, well, first start by talking about something called that we call sediments, right? Sediments are basically the broken down, weathered, physically weathered or chemically weathered remains of what were bigger rocks. So bigger rocks made into smaller rocks, basically. And those smaller rocks come in a variety of sizes. And when you're in class next week, I'm going to show you how we sieve, and then we're going to look at sediment fractions, and we're going to describe them. And that's going to be one of your main activities next week, is just describing a fraction of sediment as best you can. We describe it in various ways. We describe it first by grain size. And so these are all USGM or ASTM agreed upon standard grain size terms. And so pebbles aren't the biggest ones. You can actually get the cobbles and then boulders and so forth. These are actually technical terms. And there's size ranges, diameter ranges that sort of mark these. And so pebbles are anywhere from 4 to 64 millimeters in diameter. Granules are 2 to 4. You'll see that the 4 carries over, and then coarse sand is anywhere from half a millimeter to 2 millimeters. Beyond that, they start becoming really hard to see, right? But we can still measure them and we can still sieve them, and we'll go through that process in class. And I'll make sure we do a video of that for you folks who are virtual. Silt and then clay. And clay are the most mysterious because we can't see that at all. Not with the naked eye. We have to look at them through scanning electron microscopes to see what's going on with the actual little clay platelets. But that's how we do it. We can also describe soils based or a sediment based on the rounding of the materials. Are they well rounded or are they angular? That tells us something about how long that sediment has been a sediment. In other words, has it been broken up recently, in which case it's probably pretty angular in shape, or has it been bouncing around and hitting other things for a while and is more well rounded at this point? And this is, I sometimes use a silly metaphor. It's like people. We're all born this way, right? And then life brings us wisdom and experience, and eventually we become well-rounded individuals. So anyway, another way to tell the maturity, and we use the word maturity of a sediment, is to look at its sorting. Is it all the same size, or is it poorly sorted? And that tells us something about the maturity of the sediment as well. It tells us something about where it is in terms of like where it came from initially. So the sediment may be near where it originally broke up, in which case it's probably poorly sorted, or it may have been through after being applied to water and so forth. And the flow regimes that tends to sort things out over distance. And then finally, of course, what's actually in it? What's actually in it? So these are the big things I'm going to be asking you to describe in some sediment samples. And I've got virtual samples as well as the samples you'll look at here in class. All right, and we tend to, in the terms of soils, we tend to plot them on these special diagrams called a ternary diagram, which has 3 axes. Ternary diagrams are cool. They're one of my favorites because you have actually, instead of just 2 numbers to read on the graph, you have 3. It's very, very exciting. 3 numbers to compare, right? So we usually think about it in terms of clay, silt, and sand. So we don't include granules and pebbles. We just look at the clay, silt, and sand fraction because in most cases with soils, those are the 3 things you're looking at. And so if I have 100% clay, I plot that over up here, and obviously I have 100% clay, but I might have 80% clay, and then I might have 20% silt. If I have 80% clay and 20% silt, then I don't actually have any or 20% sand rather. Then I don't have much room for silt. I only have 10% silt. So if I'm plotting in any one of these places, if I'm plotting within the clay regime, I'm going to have 3 numbers adding up to 100% no matter what I do. And the clay, silt, and sand fraction are going to add up to 100%. So again, we're ignoring all the bigger stuff. We're just looking at the clay, silt, and sand in this case. And so these terms that you'll learn about with soils, a loam is a nice even mixture of sand, silt, and clay. A sandy loam is a little sandier loam, or a silty loam is a little bit siltier loam, where the silt content's a little higher than 33%. That's where these terms come from. And so you're going to have an activity eventually where you're going to be looking at on here it's going to come up as a little quiz, but where I'm going to ask you to show us that you know how to read these things. But this is an important diagram, so that we use this a lot. We'll be doing some ribbon testing. You'll be doing that with Mrs. Bates. We're going to do some dry sieving, and then we're going to try to settle some sediment in a large graduated cylinder as well and see how that works. And these are different ways of settling out the clay, silt, and sand fraction. So we're going to talk about Stokes' law as well, which is another way to look at this. And so that'll be another little activity that we'll look at. All right. Soils over time begin by breaking down the bedrock and through weathering. And they grow upward, but they also then, plants begin to grow on them, and animals interact with them and so forth, defecate, things like that. All that material is organic material that begins to accumulate on the surface. It doesn't get washed away. Over time, it accumulates, and then so the soil actually grows downward as well. So soils are basically growing in 2 directions, if you will, if you want to think about it that way, or developing. But it takes thousands of years for a soil to fully develop, if they ever really fully develop, right? And soils have structures that are a result of the processes going on within them. They can have color variations based on, again, the chemical processes and physical composition of materials in them. And so we'll learn how to classify colors using Munsell color charts. That's a Mrs. Bates thing mostly. And what some of those colors mean, what some of those soil structures mean. These are all important things. But of course, water is still moving through these soils, and water is going to be transporting solid materials and dissolved materials. Okay, the solid materials we say are being transported typically downward, and so are dissolved materials, either through leaching or eluviation. And so those are the big terms here. So the leach. So you can develop into they don't ever look this nice, right? But basically they'll usually blend into each other. The bedrock all the way up to the topsoil with the organic layer up here in the humus. Leaching is the downward transport of dissolved salts through the soil as rainwater percolates down into the soil. And then eluviation is the downward transport of stuff that's carried with it, right? Like clay particles, things like that, non-dissolved things. And that accumulates over here in the alluvial area, or where that's why you have so much clay in your soils, and soils around here, like I know in my yard, I'll dig down to a certain layer, and I'll hit this yellowish layer that's just really, really hard and full of clay, and that's essentially the alluvial zone. That's the It's either an E horizon or it's a B horizon, perhaps. But it's either way, it's hard to get through. Usually, it's pretty full of clay. But the horizons that develop first, obviously, are R and then O. Eventually, A will develop because you start accumulating organic matter, and the C will develop. These B and E horizons take a lot of time, and those don't develop right away. They take a fair amount of time to develop. But if you do Envirothon, that competition, one of the big events is actually understanding the soil profile, and so this is pretty important stuff. You can be a soil scientist, and this is what you do, right? This is important. This is really important for farmers. It's really important for engineers, civil engineers, among other people. And here's a better example. Here's an actual example of a soil. So I have a couple of gigapans that I'll share with you as well, and actually ask you to try to identify the horizons. But again, you have the various horizons here, and you can imagine if you can identify them. This one does not include an E horizon because it develops later. There may not be an E horizon in the soil. There's also subhorizons. You can have an E with another little letter sometimes. It can get really complex. We're not going to go that far with it, but it can get really complex. So we can classify soils, again, based on climate, right? Climate and parent material and slope and the other things that determine what a soil looks like and what its composition is. We can classify them. There's 12, there's 10 plus 2 or soil orders out there. And then there's also the soil series, which is the lower level of classification. But these are the 12 soil orders. So like things like andisols are typically volcanic soils, for instance. Oxisols are often very tropical. And then mollisols, we have some of these out in like northwestern Ohio. We get the really nice, deep, dark, black, organic rich soils. So these develop because of the climate, but also because of what the rock is that's nearby that's being developed from, and other factors, of course. So the factors that are involved with these soils are these. So parent rock and climate are very important. We talked about climate with weather, and we know that moisture and temperature are very important. We also know that the rate of plant growth and decay is important, which is, of course, greater in the tropics than it is in, say, the Arctic. Slope aspect, the direction the slope is facing, north, south, east, west, and how steep it is are both important. Time, you got to have a lot of time for this to occur. And then whether the stuff's being transported away, how much erosion is going on. And that's important to note also. So here's an example. This is where slope aspect, which is something that you don't think about most of the time. But if you go see where certain ferns might be growing on the northern side of a slope, or moss on the northern side of a tree around here. This is an example of that. At this particular location, we have grasslands on the south slope, and then you have more north-facing slopes full of trees, and that's obviously going to produce a different soil. So we're going to stop there. We could get into mass wasting processes next. These are big erosional processes, but we're not there yet. So we're just gonna focus on the soil. So great, thanks for paying attention, guys, and I'll see you in class.